Hi everyone, welcome to Differential Calculus. Today we explore lesson 4.1, maximum and minimum values. Number 1, local versus global or absolute extreme values. Definition. Let C be a number in the domain D of a function f, then f of C is a global maximum value of f on D if fc is greater than or equal to fx for all x in D. A global minimum value of f on D if f of c is less than or equal to fx for all x in D. F of c is a local maximum value of f on D if fc is greater than or equal to fx when x is near c on both sides. And fc is a local minimum of f on D if fc is less than or equal to fx when x is near c on both sides. Well, that is the definition. Let's take a look at an example graphically. Okay, we have the graph on the left side. And it is a graph of a function on a closed interval. So we have two endpoints. According to the definition of local maximum and local minimum, there is a local maximum because locally it is the tallest or the highest output. So right here, this point right here, this is the local max. Similarly, there's a point at the bottom of the curve, and this is the local min. So when we look at the graph itself, the smallest output in the domain is the global minimum. So we have this point right here to be the global minimum, and the biggest output is the global maximum. So right here is the global maximum. Yeah. Here come a different example on the right side. Similarly, we have a graph and the domain is a closed interval. So from one endpoint to another. Locally, there's a point on the top of the curve, and we have a local max. There's a point on the bottom of the curve locally. So that gives us a local minimum. Well, and in this case, we got to compare to the output of the two endpoints. Take a look at the overall output. We see that the global minimum appear at the local minimum right here, because it is the smallest output. And the biggest output is at the local maximum, global maximum. So sometimes the local minimum and the local maximum, they are the global minimum and the global maximum. We need them in order to determine the extreme values of the function on a closed interval. Okay. Number 2. Local min-max and derivative. From the 2 examples, notice that for a function f to have global or absolute min and max values, the function must be continuous on a closed interval. And at the local minimum and maximum values, the slope of the tangent line is 0. So that tells us, in order to figure out the local min-max, we set f prime x equal to 0 and we solve for x. Here's the question. Does f prime c equal to 0 tell us that c is a local minimum or maximum? Now to be careful with this one. There's the function fx equal x to the 3. And the graph of it look like this. At x equal to 0, we have a horizontal tangent. What this means is f prime of 0 is equal to 0, but the function is increasing. But f of 0 is not a local min or max. Here comes another example. Fx equal to absolute value x. X, y. This is the absolute value. At x equal to 0, but f prime of 0 does not exist. Well, which means that we got to be careful on define the number c that will give us a local minimum or maximum. Let's move to 3. Critical number and the extreme value theorem. Definition: a critical number of a function f is the number c in the domain of f such that either f prime c equal to 0 or f prime c does not exist. So that is how c is defined to be a critical number. And with this definition, we have the extreme value theorem. If f is a continuous function on a closed interval a to b, then f has a global minimum and a global maximum. To find the extremum, we do 2 steps. Step 1, find all critical numbers in the closed interval a to b. Step 2, find all output of critical numbers in the closed interval a to b and the endpoints. The smallest output is the global minimum, and the largest output is the global maximum. Let's do some example. Example, find the global or absolute extremum of fx on the given closed interval. First example, we have fx equal to x to the 3 minus 3x squared plus 1. First thing is step 1, find critical number in nib 1 to 1. Critical number is the, we set the derivative equal to 0, so the derivative is the 3x squared minus 6x set equal to 0. Then from here we can factor the 3x, x minus 2 equal to 0. So we have a 3x equal to 0, x minus 2 equal to 0. So x equal to 0, x equal to 2. Well, 2 is not in the closed interval. Okay. Move on to step 2. Find output at the endpoint and also at the critical number. So that would be a f of negative 1, f of 1, f of 0. F of negative 1 is negative 1 to the power 3 minus 3 times negative 1 squared plus 1, which is negative 3. F of 1, we have do the same substitution. 1 to the 3 minus 3 times 1 square plus 1, negative 1. F of 0 is 0 to the 3 minus 3 times 0 square plus 1, 1. The smallest output is the absolute minimum. So negative 3, absolute minimum. The biggest output is the absolute maximum. Pretty cool. Another one, fx equal to root x e to the x on the interval from 0 to 1. Okay, first thing here is look at the root extract. For this one, we can quickly say that the domain is from 0 to infinity because we do not have a square root of negative number. So now let's do a f prime x. That is the product rule. E to the x multiplied to the derivative of root x plus root x multiplied to the derivative of e to the x set equal to 0. Ex times 1 over 2 root x plus root x ex. So that's 0. You can factor out e to the x 1 over 2 root x plus root x equal to 0. Well, e to the x is not equal to 0. So the remaining factor has to be 0. E to the x more than 0. So 1 over 2 root x plus root x equal to 0. And then from here, we can multiply by root x. And we can only do this for x greater than 0, because it will balance out the equation. 1/2 plus x equals 0. X equal to negative 1/2. Negative 1/2 is not in the closed interval 0 to 1. Notice that f prime of 0 does not exist. So x equal to 0 is a critical number. Okay, we just finished with the step 1. And here comes the step 2. Well, it looks like the critical number is also the end point. We have to do f of 0 and f of 1. F of 0 is the root 0 e to the power 0, which is 0. F1 is root 1 e to the 1, which is e. And then from here, it's pretty clear that 0 is the global minimum. E is the global maximum. Let's do another example. C. Let's take a look at the quotient here. Fx equal to x over L1x on the closed interval 2 to 4. Let's be careful with the domain here. L1x is 0 when x equal 1. So the domain of this function is from 0 to 1, union 1 to infinity. Now we can do f prime x. It's the low d high L1x multiplied to the derivative of x minus high d low x times derivative of L1x over low square L1x square. Set equal to 0. L1x minus x times 1 over x over L1 x square equal to 0. L1x minus 1 over L1x square equal to 0. Well, the denominator cannot be 0 because of the domain. We restrict the domain here. Thus, only the numerator can equal to 0. L1x minus 1 equal to 0. L1x equal 1. Take e at the base. And from there, we have x equal e. And e is 2.7 something. So it is in the closed interval. That's it. We just finished the step 1. Here comes the step 2. Let's plug and chug. Only a few numbers here. Well, f of 2, do the substitution. 2 over L12. And that is 2.885. F of 4, 4 over L4. Well, that is also 2.885. Wow, pretty amazing. f of e is e over a1e, which is e over 1. That is 2.718. From here, we see that we have a 1 absolute max and 1 absolute min. Thank you for watching. I hope you found the content useful. Please like and subscribe to help the channel growth. I will see you in the next video.